Hi, everybody. Okay, lastly today, I'd like to do an example. I'd like to show you that because a changing electric field creates a magnetic field and a changing magnetic field creates an electric field, that we can get electromagnetic oscillations that can persist in time inside of, say, a closed metal can, okay? Like this can here, if it didn't have any soup in it. All right? Now, this is interesting in and of itself, but it's also interesting because, well, these oscillations, they're kind of like electromagnetic standing waves. And in the next couple of lectures, we're going to lead up to and talk about electromagnetic traveling waves or light waves that move through space. So in some sense, this is a starting point. Anyway, that's the example. Here, hang on and we'll get started. Okay, so we're going to talk about electromagnetic oscillations, which occur because a changing magnetic field creates an electric field, and a changing electric field creates a magnetic field. Here, let's write down these laws. So suppose we're in a charge-free region. Then, as we know, a changing magnetic field will create an electric field. As described by this equation. Or alternately, and more usefully for the problem we're going to do, we can say that the integral of the electric field around a closed loop is equal to minus the rate of change of the magnetic flux enclosed by that loop. So Faraday's law. Likewise, we have our modified Ampere's law. In a current-free region, this says that the curl of the magnetic field is given by mu naught epsilon naught by the rate of change of the electric field. Or expressed as an integral equation here, it says that the integral of the magnetic field around a closed loop is given by mu naught epsilon naught times the rate of change of the electric flux. Okay? So with that idea, let's consider the following problem. Let's consider a pair of metal plates separated by a gap. Which can be driven by an AC power source. Okay? And initially, at least, let's think that the power source, the voltage at the power source is V0 times sine of omega t. So, of course, this is going to produce an oscillating charge on the plates, and thus an oscillating electric field between the plates. The first approximation, at least, the electric field between the plates should also vary with time. So that the electric field is equal to E0 times sine of omega t. And at least at the point between the plates, we expect that E0 should be equal to the V0 divided by the distance between the plates, L. Okay. Oh, and as long as we're setting this up, let's also call the radius of the plates R. Okay. Good. Now, what I'd like to do is investigate the induced magnetic field between the plates. And then we're going to look at the induced electric field between the plates. Sound good? Here, let's talk about the induced magnetic field. Okay, to consider this, it's helpful to imagine looking down at one of the plates. Okay? We see that there's an electric field between the plates. And at least at the center of the plates, we know what the value of that is. So the electric field will oscillate in time like E0 sine of omega t, where at least at the center of the plates, the strength of the electric field should be V0 over L. To find the induced magnetic field, we can construct an Amperian loop that has some radius r, and that encircles a certain amount of electric flux. Okay? Then what we expect is that the integral of the magnetic field around that loop should be equal to mu naught epsilon naught times the rate of change of the electric flux. Right? Now, on the left-hand side of the equation, the integral of b dot dl should just be, because of the symmetry of the problem, 2 pi r times the magnetic field at that distance from the origin. Whereas on the right-hand side of the equation, we have mu naught epsilon naught times the rate of change of the electric flux. And the electric flux, we assume, is just equal to the area enclosed by the loop, pi r squared, times the electric field there, E0 sine of omega t. Okay? And simplifying this, we get pi r squared mu naught epsilon naught times E0 times the rate of change of sine of omega t, which is just omega times cosine of omega t. And finally, solving for b here, we have b as a function of r is equal to, well, it's the right-hand side of the equation divided by 2 pi r. The pi's cancel, one of the factors of r's cancel, and we're left with 1/2 times mu naught epsilon naught omega E naught cosine of omega t times r. And this field actually points in the phi direction around the circle. Cool. Okay. Now let's look at the induced electric field. Because of course, a changing magnetic field is going to induce an electric field, all right? Now to look at this, it's helpful to make a slightly different drawing. We'll look at the two plates as seen on edge. Okay? If we use the right-hand rule in the first part of the problem, we can see that the direction of the magnetic field here is into the page on the right side, and out of the page on the left side. Okay? Moreover, you can see that the magnetic field is 0 at the center, but it gets stronger and stronger the farther we get away from the center because the strength of the field varies like R. Okay? Now we can use this drawing to calculate the electric field. Here, let's draw another Amperian loop. This one is going to be interesting. One side of the loop will be here, and the other side will go out to a point very, very far away from the loop. That is, it'll go out maybe to infinity. Okay? And then we want to figure out the integral of the electric field around that loop. Okay? Now, first of all, we know that the integral of the electric field around a closed loop will just be minus the rate of change of the magnetic flux through the loop. Okay? We'll turn and look at that in a second. In addition, because we know that the strength of the electric, that it's the curl of the electric field that's related to the rate of change of the magnetic field, we can see that in this problem, the electric field and the magnetic field have to be perpendicular to each other. Okay? And in fact, the electric field between the plates has to point vertically in this drawing from one plate to the other. What that means is that the integral of the electric field around the plates, let me say around the loop, will look like the following. It'll have a term on the left side, which is just E times the distance between the plates, L, and then the terms on the other sides will be 0, either because the loop is perpendicular to the direction of the field, or in the case of the side that's infinitely far away, because we know that the electric field from the charged object will be vanishingly small when we're very, very far away. Meanwhile, on the right side, we have minus the rate of change of the electric flux. Okay? Now, in this case, we have to do an integral. Over the surface enclosed by the loop to find the electric flux. Okay? I'm sorry, magnetic flux, excuse me. All right. And so that'll occupy us for a moment here, but it's not hard at all. The integral of the magnetic flux here, enclosed by the loop, is just given by the following. So okay, it's given by, well, we have minus rate of change okay, excuse me, minus the rate of change of the integral from z equals 0 to L of the integral of r equals 0 to the radius of the loop of the magnetic field, which is 1/2 mu naught epsilon naught omega E0 cosine of omega t times r dr. Actually, almost all the terms can be taken outside of the integral. So we have minus, and likewise, most of the terms don't depend on time. So we'll just have minus 1/2 mu naught epsilon naught omega E0, okay, times derivative with respect to time of cosine of omega t, okay, times the integral over r of r dr. All right? Finally, we can imagine that when we're in between the capacitor plates, there's an electric field, and the changing electric field induces a magnetic field. But once we're outside of the area within the plates, there's no electric field anymore. So there's no induced magnetic field. So our integral here to enclose all the magnetic flux should run from 0 to r. Okay? The integral over r gives us capital R squared over 2. Excuse me. And then the derivative with respect to time of cosine of omega t gives us omega, or times minus sine of omega t. The minus signs cancel. We get another factor of omega, and then we have sine of omega t. Okay? And we forgot to do the integral over z, but that just gives us a factor of L. Okay? Very good. The L's cancel. Oh, excuse me. And we have the following. The induced electric field, I'm sorry, is equal to 1 over 4 times mu naught epsilon naught r squared omega squared times E0 sine of omega t. Okay? Great. Okay, so here's what we've done so far. In 2 steps, we found the induced magnetic field and then the induced electric field created by the changing magnetic field. And we got this expression here. Okay? Now, what I want to drive home to you is that according to this formula, under certain conditions, the induced electric field will just be exactly the same as the original electric field. And if that's the case, then this oscillating field can sustain itself. Even if we first set up the field with our power supply and then take the power supply away, okay? If this were perfectly conducting, the electromagnetic oscillation that we set up would persist indefinitely. So in order for that to happen, the induced electric field must equal the actual electric field or the initial electric field. That is, E should cancel with E naught sine of omega t. Okay? So that we have 1 equals 1 over 4 mu naught epsilon naught r squared omega squared. Okay? Actually, this is a condition on the frequency of the oscillator. Okay? It says that omega must equal, omega squared must be 4 divided by mu naught epsilon naught r squared, or omega must be 2 divided by square root of mu naught epsilon naught r. Or jumping ahead a little bit and noticing that that factor of 1 over mu naught, square root of mu naught epsilon naught, that's actually the speed of light, we'd find that omega has to be 2c over r. This is the condition, apparently, to create this electromagnetic oscillation inside of this can. Okay? We can have it, but only at certain frequencies. And apparently this is the formula for the frequency. Okay? So that's kind of neat. Now, I actually want to, now that we've said this, I want to tell you what we've done is only approximately right. there's something that we've ignored, okay? Here. Let's take a look at this drawing here again. Oops. And apologize while I fiddle around with this drawing. Here we are. Okay. We use this drawing to figure out the strength of the induced electric field at the center of the can. But if we had picked some other point in the can, we would have gotten a different answer. For example, what if our loop went from infinitely far away to this point on the outside of the can and then back out? Well, we kind of expect that when we're outside of the area defined by the capacitor plates, that there shouldn't be any induced electric field. So the electric field outside here is actually zero. And then if we make our loop a little bit bigger so that it encloses only a little bit of magnetic flux, well, then the induced electric field should actually be small. And it's only when we go all the way to the center that we get the electric field that we found. What does this mean? It means that in our electromagnetic oscillation, the electric field between the plates is actually not uniform. It's strongest in the center, and it goes to zero at the edges. Okay? But that's really brilliant in a way, because what it means is that because the strength of the electric field goes to zero at the edges, we can put a conducting wall here, and it doesn't make any difference. Since the electric field would be zero at the edges, there won't be any current that flows through the wall. So it'll be as if it weren't there. And we'll still be able to have these electromagnetic oscillations where the changing electric field creates a changing magnetic field that in itself generates the changing electric field that's responsible for the cycle. So it's a self-sustaining cycle, okay? That is, we can put the walls on our can. But the second thing about that is because the electric field is not uniform, our discussion was not quite right, okay? Our induced magnetic field wasn't quite the value that we expected, and likewise for the second part. And so because of this, the condition on omega is actually slightly different. Actually, if we do the problem exactly, we find that omega has to be not 2 C over R, but 2.405 times C over R. Okay? I hope you can forgive me. Anyway, it's a neat example, and I wanted to show it to you that electromagnetic fields can generate themselves once they're set up. And so we can have a self-sustaining oscillation like we saw here inside of our metal cavity. Okay, I think we'll stop here and I'll see you in class.